In this video, we're going to be talking about the GPS sensor. We'll go ahead and just jump right in. So our GPS is a sensor that we're all familiar with. We use it on a daily basis as we're navigating from one location to other if we're using the help of Google Maps, for example. So the Global Positioning System is a system of 24 satellites, a constellation of 24 satellites orbiting the Earth at roughly 20,000 kilometers above the Earth's surface. The constellation is designed really nicely so that any point on Earth is visible by at least four satellites. And you need at least four satellites so that you can get your position measurement. You need 3 satellites because you have 3 uncertainties in terms of X, Y, and Z. And you also have an uncertainty in terms of a clock offset. So GPS measurements we actually get pseudo range from each one of the satellites. You don't actually measure the range. You measure what's known as pseudo range, or the time of flight between the satellite and you. And so there's that clock offset that can become an issue. So we need 4 measurements to get our latitude, longitude, altitude, and that clock offset estimated correctly. There's a variety of error sources in GPS. These sources come from things down from the pseudo range, right? So that's our receiver measurement. We also have ephemeris data, so that's errors in the satellite positioning, the satellite clock. Our atmosphere is going to provide some issues as the signal travels through the atmosphere. We have multipath reception, so if you're if you're by buildings or really anything else that can reflect the GPS signal, right? So those can all provide significant sources of error. So we can try to characterize all of our error. And right here, this shows a table of components measured from this UERE sources, right? So the sources we were just talking about, and we can get a host of error measurements, or we could try to characterize the error from that aspect. We can also look at our horizontal and vertical depth of precision error, and we can then come in here and combine them, right? So here's an example. So in the horizontal plane, northeast plane, you can get up to the variance of 6.6 meters, and in the vertical, this shows 9.2 meters. So the last 2 or 3 slides, all about just characterizing that error. And so there are books written on just trying to characterize the exact error in GPS. We're going to come up with a decent model for modeling the characteristics of GPS. So the model that we look at here uses a Gauss-Markov error model to produce basically a random walk. And this random walk, this Gauss-Markov error model, has two main components. This first component is a stability component. Left alone, if you were to cross off any of the noise, this would drive V(n) to 0 as n approaches infinity, right? So it's something that's bringing the error back in. And then this component is just white noise, causing the system to move around randomly. And the value for this white noise in any of the 3 different axes can be taken from these model parameters. So we have standard deviations listed in this table. And then what we're going to do for our sensor measurement for the position sensor is we'll take our actual northeast and down locations, and then we're going to just add it with this random walk in each of the 3 directions. So we'll have northeast and our height for that random walk. And this next slide just shows some of the results of this. Really, this is showing our V of n, right? That Gauss-Markov model. And we show here in the altitude, we get all the way up to, more than 10 and down below minus 20. So, and this is in a time frame of 0 to 12 hours. The bottom axis is showing us a smaller window, right? Showing how our GPS is varying over time. It's not necessarily a white noise like we see with some of the other sensors, but we just get this slow drift in our sensor reading. Okay, we can also use our GPS can also give us readings as described over here in terms of velocities and our heading. So if we, again, this is just a review, we have our ground speed velocity and our course angle. The GPS is going to help us it can give us measurements in both the speed and our course angle. So this is just characterizing the noise. The noise that comes into play. And then we get these are our two sensor readings that come out of the GPS. So we have a GPS measurement of our ground speed velocity, right? And our GPS measurement of our course angle. So we get these two simple models for defining or for getting those measurements out of the GPS. So with the position, which we're very familiar with, and the reading of our ground speed velocity and our course angle, that just about sums up a really brief overview of GPS.